And happy Wednesday to everyone. Great day here in the Central Coast, so hopefully you will have time to enjoy that, or you already did enjoy it, should you be watching this at a later time. We are rolling here in the middle of week 2, so just by way of reminder, we've got PLC 2, which is posted. That's going to be due Friday. Same format as we had last week. Quiz questions, answer them, see how you go. Homework 1, we're still looking at Tuesday as the due date, and on that day will be the first problem style homework quiz. Today though, we do have a concept quiz enabled. So there's a concept quiz that's up and going, and that is due by midnight tonight, time limit of 1 hour on that. And a few things I got left to fix up on doing that. If those of you who have ASC, I have not actually gotten to that, so be patient please while I get that established. But when I do, if you have ASC, then use the ASC link and not the regular one. You will be assigned 2 quizzes, just use the one that has ASC on it. So that's going to be going today, just working on some drawings, some explanations, see how you do, okay? The time limit does include starting, uploading, doing whatever. There isn't really an upload because there's no file, I just put the questions in there, but getting that started, and then also that would be downloading, I guess, and then uploading whatever files you want to send. That is included in the time limit, so please be aware of that and manage your time. You may want to stop a few minutes before in order to accomplish that. If your internet's a little wonky, you may want to leave 10 to 15 minutes to do this, okay? So just be aware that time is built into the actual time for the quiz itself. And so we're going to continue on with what we were talking about yesterday, which was total internal reflection, and a quick summary that we have going here. And then I got a couple of demos here that hopefully you'll be able to see, but I think it worked out okay last time with the laser. The computer camera does tend to mess things up, but we worked with refraction and Snell's law last time. And so thinking about what we had going, okay, I had a situation where I had a medium in which light could travel faster, such as air, a medium in which it could travel slower. I think we picked glass or maybe plastic or something like that. We had a light beam coming in like this, measured to the normal. Just setting this up here, our incident angle. We found that since the light speed is slower here in glass than the light speed is in air, we would find that the light ray actually bends towards the normal, and it lowers this angle compared to the incident angle, okay? So you might say that air has an index of refraction, say N1 here for air, of, we would say, approximately 1, okay? Is it a bit, yeah, it's an approximation, okay? Yes. It's not exactly like, but it's really only like 0.3% off, so we're gonna call that good. Glass, we have an index here. It's gonna be about 1.5, say, something like that, okay? Which means that light's traveling only at about 2/3 of its normal speed. And when that happens, remember the wheels, right? If I'm rolling the wheels in, this one catches first, that one's keeping going, it turns downwards, so it shallows the angle out. Okay? We also ran into total internal reflection, which happened were I to reverse this path. Okay? Remember, internal reflection only happens going from slower light speed to quicker light speed. And that means that you have the opposite going on with the index, right? Because the faster the speed, the lower the index, down to 1, obviously, right? Of course. So the slower the speed, the higher the index. Or I should go, slower the speed, the higher the index. The higher the speed, the lower the index, right? It's one of those opposites. So as I look at the glass index here and I say, okay, if I started light in the glass and I tried to get light into the air, which would be the exact opposite of this, it'll work for a while. And then if I start exploring different angles, I start putting it in at an angle that's out here, right? If I just, maybe I'll just do another sketch of this real quick over here. Okay, so now here I am in glass down here, and I'm starting to go out like this. Here I am in the glass with an incoming ray that looks like that. And now if I check the normal, all right, it's going like this. And you'd recognize that if it came in at that angle from the air, it would bend towards the normal a little bit more, so that would be an okay path. But what if we kept going with this angle, right? If we kept going with this angle, we'd be soon out here, and then we'd have something like this. And then we'd have something like this. And there's going to come an angle at which this refracted ray basically never leaves the material, the glass in this case. And so when that happens, we say, let's see if I can draw one more in here, and it comes out directly that way. But when that happens, I'm going to make a big right angle all the way down from there to there. And that means that all the way from here to here, that's the critical angle. Okay. Now, we were just having this discussion a little bit. This is a refracted ray, and it does not technically exist. Okay. So what happens when this goes that way at this angle is that you bounce it off at this angle here, and that angle is the same as this angle here. So what happens is that we say that the refracted ray comes off at 90 degrees, but there's really no ray here, okay? There's no ray here. The ray is getting reflected, and it's supposedly it would be at the same angle. Hopefully I got those reasonably well in terms of size, okay? Okay, couple of, let's see, couple of demos here for you. So last time we had the block of plastic and I was shining the laser in, and it was reflecting off the lower face. I think it was this way. We're going reflecting off the lower face. I have here another piece of something which is relatively the same type of thing, same type of material. And if I shine the laser in, I don't know how well we'll see this, but if you take a look at this, it's got a bend here that's, I'm going to point that towards you, and then I'm going to shine it in from this side. So it's almost like one of those curly straws. So it goes around and then pops it out this way. So if I shine the laser, okay, if I get the laser going and I shine the laser into this thing, I'll hold it by this so you can see a little better. If I hold it into here and I go there and I just go like this, can you see the internal reflections? I think you kind of can. Well, that's not too bad. If I hold it steady and I go up a little bit more, well, that's saturating a little too much on the upside there. But you see the first couple, all right? Also pay attention to this spot right here. I'll try to put it right in the middle of the circle so you can see it a little better. And if I go there, see how well it's glowing? Yeah. Notice that no light, well, okay. Light is leaving this because we can see it, okay, yes. So it's not perfect, but nonetheless, most of the light that I'm shining into this thing is in fact coming out towards you in the middle of the circle there. All right, happy, happy, joy, joy. There we go. See, you got a pretty good reflection going on in there. I can just turn it. And it's also reflecting around the circle. And it's tough to see that part of it. But nonetheless, that is happening. So this is actually this actually is fiber optic material. It just hasn't been squeezed down. What they do is they extrude it. They pass it through smaller and smaller holes when it's heated, and then it comes out thinner and thinner and thinner. Or they take it and stretch it or something. I can't remember what they do. So that actually is in about a couple hours, that is going to turn into this, which here, I don't know if you can quite see that. If I hold, whoa, hey, let's not do that. Okay, so if I hold this and I see, maybe on the back, on my shirt, maybe you can see it a little better if I hold it with the background that's a little darker. This is actual fiber optic cable here, right? So they make that stuff, they make this into these by slowly extruding them, really tiny. So here's the fiber optic cable, and we've just nipped off the end of it here. And so we will see if we can get anything good from that. If I am careful and go there. Well, there. Oh yeah, you can see that. It's, I have to look down here and then look up there, but that, yeah, you can see that pretty well. If I turn it this way, right, I'm shining the laser in down here and it's coming out, whoops, let's try to do that. It's coming out up there, or no, when am I shining it in? Dang, this thing's bright. Okay, oh, I can't even see anymore. Where is it? Where is it? Where is it? Where is it? Oh, had it there for a sec. How about there? Okay, there we go. Getting it. The laser's actually off the screen right now. So you're seeing the laser emerging from the end of the fiber optic. And if I maybe turn it this way, I wonder if you can see it a little better that way. Not really. Well, kind of. Yeah, maybe, kind of, sort of. A couple of bonds. They're all lighting up right there. Anyways, happy days. Good times. Another piece of fiber optic just kind of squinched into a crazy thing. Here's, yeah, you can't see the end of that, but you can see the beginning of it. You see it bouncing back up and forth in there, up and down. Yeah. Okay, whoa, that laser is really bright. All right, so a couple of examples of internal reflection. And it really is internal and total. So the reason you have this cladding on the fiber optic is so that they have engineered, somebody's taken some time to think about what's going to work best, right? With an index inside the material, and then what's it going out into, okay? So you know you want the lower index as you go away from the material that carries the light. So it goes into a lower and lower index, and then they put the cladding on here to try and really help the signal stay. And it really does work. You can transmit a signal thousands of kilometers with this wire, right? All you got to do is have the wire. And those of us who were around and possibly making transatlantic phone calls back before fiber optics were a well-known, useful technological tool, the difference was night and day. Once they installed the fiber optics on the bottom of the ocean, and then we were able to have phone calls go back and forth, oh, it was like the person was like standing right next to you. It was amazing. Comparatively to what it used to be. Of course, nowadays, we do different things. All right. So there's that. And last time we did an example of finding the critical angle using Snell's law, and we did an example of just regular refraction and just trying to chase through a light beam. I'll call this 1, let's say theta I, and that's N2 times sine theta R. We tried to find some angles using the Snell's law here, and we also found a critical angle last time. So yeah, that's basic refraction. We're going to now use this to go into talking about lenses, in which we're going to construct a particular curved surface out of glass such that, which is still transparent, such that the light that goes through it refracts and comes out in order to make an image. And now we're going to go and talk about lenses in the same way that we talked about mirrors. And we have this behind us. This is a little bit more scaffolding to talk about refraction, because refraction is a little bit more complicated than reflection is. Reflection is just angle out equals angle in. And we're done, right? And all you got to do is polish up a surface, make it nice and shiny, and all of a sudden you got a mirror. Well, this is a little bit different. You're thinking about the index, you're thinking about the light speeds, you're thinking about the angles, right? And now we're going to start talking about how to get lenses to give us some images, all righty? So, let's do that. The good news here is that more or less, if you are able to kind of widen your thinking out, everything is exactly the same as it was for mirrors, okay? That means the three rays we use for the ray diagrams are basically the same. The mirror equation is now going to be the lens equation, or really I should say the thin lens equation. We're going to add one more thing on top of the thin lens equation. Also the magnification is the same. We're going to add one more thing on top of that, maybe by the end of today or maybe at the beginning of tomorrow, just to get a better handle on how to shape the lenses. All right, so let's take a look here. We're going to talk about lenses, and I want to qualify that by saying that we're going to talk about lenses that are pretty thin, okay? At least we'll start off talking about lenses that are pretty thin. The reason for that is that it makes the ray diagram drawing much more simple. Remember what we started off with mentality-wise when we looked at the mirror, right? We had the mirror drawn and then we went to curved mirrors and we said, well, the law of reflection is still the same, okay? But it's kind of a hassle to follow a normal. We got to drop a normal on top of the curved surface and then make sure I've got the incoming angle. I've got to get the outgoing angle, make sure it's the same as the incoming angle. And if you're going to do that for every ray you draw, it gets to be cumbersome. So we developed these rules that if the light was coming in parallel with the axis, it goes a certain direction, right? Through a focal point. And likewise, if it starts by going at or through a focal point, it's going to come out parallel, right? So we developed these rules that kind of shortcutted our need to get out the protractor and make sure the reflected angle is equal to the incident angle. We're going to do the exact same thing here. And that's why we're using the same three rays. Because we don't want to have to do this every single time. Okay? So it's the same three rays as reflection. All right, so I'll draw you a converging lens example here. All right, and oh, incidentally, we'll use converging lenses and diverging lenses. Just exactly in the same way as we did with converging and diverging mirrors. And pretty soon you'll see why I call them these rather than the concave and the convex. All right, so let's take a look at a converging ray diagram. I'll draw this out for you. Same basic setup as with a mirror. I'm going to have a lens. Let's get the lens here. Okay, so I'm going to get the lens here. I'm going to go like this and like this. All right, a converging lens looks like this. Sorry, quick. There's something happened to my pen here. Okay, a converging lens looks like this. Why? Well, I somewhat sketched it out a little bit for you, but just by way of explanation as to why a converging lens should look like this shape, okay? Let's blow up. Let's take a look at the top part of this and just kind of expand it out a little bit. So there's the top view, zoomed in. No, or it says not the top view. This is a zoomed in view of the top piece. All right, this is top. All right, closer view. All right, that's closer view. It's not the top view. All right, look, we're gonna do this. I got the, all right, here comes the lens like that. All right, nice big thick piece of the top of this thing right here, okay? Now, if I have an object that's way over here and it's broadcasting its light as it usually does, remember, light hits something and diverges away, okay? It acts like a point source of light. So, suppose here comes a beam of light. It's coming out from here, going like this. It hits right there. If I'm careful and I use the law of refraction, Snell's law, I'm going to drop a normal to the mirror here. Let's see. Can you see the? Is the green coming in okay? It looks a little bit too smooth. What about the black? Oh, that does not feel like it's. Oh, it's about the same. All right. I'm going to drop a normal right on the surface here. Now notice the surface is kind of curved, right? So I'm going to be careful. My normal will not be horizontal here because it's not that shape right there. It's more like here. Make it kind of nice and longer so you can see it. So that's my normal to the surface. And now since I know that the light's going air to glass, it's going to bend towards the normal. So I'm going to find that it goes like this. Say, it goes that way. Now I'm going to go over to the other side. I'm going to drop my normal across that. But notice it's not the same direction as this normal here. It's going to be in this direction here. I'm trying to get this darker. Like so. Can you see that? Oh, just barely got it up there. All right, just before the glare. Now, since we know we're going glass to air, the ray bends away from the normal because I'm dropping the index. So I'm making the angle larger, okay? So here goes the ray. It's going to go that way, like that. And you can see that this is going to result in something in which the convergence is going to be the convergence is going to be the thing that's happening, okay? How do we know that? Well, as we drop further and further in, right, the light's going to be coming in at more of a shallower angle, less of an angle here, and the normal is going to be shallowing out. So I'm going to get less refraction, right? I'm going to get less refraction, which means that more or less the ones that are down here are kind of going a bit straighter, and the ones that are up here are getting pulled down, and then the ones that are coming in down here, they're getting pulled upwards. Same exact thing, right? If I just flip that over, I find the exact same thing happening. I have a light beam coming this way, getting refracted. And so this is a converging lens. I'm going to pull a symmetry axis over here. Okay, just like I did with the mirrors. And I'm going to note there's a slight difference between the lens and the mirror. Number one, the number of surfaces. Okay, I have two curved surfaces. I have two curved surfaces for the lens. Okay, that means each one of them carries its own radius and therefore its own focal point. Okay, now I'm going to make the radii equal, so we'll have equal focal points on both sides. And let's suppose that I've got a focal point here and a focal point about here. Where's that one? 1, 2, 3, 1, 2, 3. Yeah, it should be here. There's focal point. Okay, so that just because one of the F, make it bigger. There we go. Focal point there and a focal point there. So now when I have an object, I'm going to start with my object in the usual configuration. It's going to be out here, and then the light's going to be coming left to right. I'm going to start with an object out here, outside the focal point of the lens, and I'm going to imagine the light is coming away from it. As we talked about with the reflection, there are an infinity of rays. They are going in an infinity of directions. That's too much for us to deal with, so let's just pick a couple. How about the three rays that we know about already? Let's start with a ray that's coming in parallel with the axis. Okay? Let's start with a ray coming in parallel with the axis, and that's going to be this one right here. Whoops, it's a little wavy. Now, I'm going to make an approximation. Remember the thin lenses. Notice I drew that ray all the way into the lens, and I didn't deviate it. Remember, I don't want to have to do, oh, I should do that. I don't want to have to do this on every single ray that I draw on every single ray diagram. So, we're going to make the approximation. We, not just me, you are going to do the same thing, that the refraction happens all right in the middle of the lens. And that way I don't have to draw the little bump, bump, right? And I don't have to drop two normals because I'm following rules. And the rules are, because the geometry is exactly the same as it was for a mirror, a ray that comes in parallel with the axis is going to leave through the focal point. Now remember, this is not a bouncing off situation. This is a passing through situation because the lens is glass. It's made of a transparent material or plastic, right? It's not silvered. So we are not concerned with a reflection here. We want to think about the passing through of the rays due to refraction. So when I do this ray, what I'm going to do is I'm going to have the ray coming down and going like that. Oops, a little hitch in the middle there. Okay, so I'm going to have all the refraction just happen right in the middle of the ray, right in the middle of the lens, so that the ray changes direction there, and it just does both of these things. Oh, I got to remember how to do this. It does both of those things just all at once. Okay, so this would be our ray number 1. Ray number 2, if you remember ray number 2, it bounced off the point at which the mirror and the symmetry axis intersected. So let's do the same thing here. We're going to go to the point where the lens and the symmetry axis intersect, but remember, we're only going through the middle point. So, again, it's an approximate situation, but it is definitely going to be enough for us to deal with. And I'm going to have my straight edge for this one. I'm going to go straight through the middle of the lens, and it's going to be undeviated. There's no refraction that I'm going to really be concerned about here. I'm going to go with, I think it's going about there. Coming down through the middle of the lens. Oh, I tipped it. Man, I had such a good run going too, and now it's freehand. And this would be ray number 2. Right? It's going right through the middle of the lens, undeviated. This is the equivalent to the reflected ray coming in and then leaving at the same angle on the mirror side of things. Okay? It's going in and leaving at the same angle. Right? That's the same idea. Now, would there be refraction there? Yes, but remember, we're doing a slight approximation here, all right? That would be ray 2. So this right here is enough for me to find my image. It's right there. I've crossed these two rays, so I know that the image is going to be here. Where my two rays cross. Now, I'm just going to, for the purposes of our situation here, we had 3 rays, so I'm going to put in ray number 3. You really, right, need only 2 of them. Ray number 3 was the one in which it started, if I'm thinking converging mirror, it started by dropping through the focal point, hits the lower side of the mirror, and then comes out parallel with the axis, right? So we're going to do the same thing. I'm going to hit the first focal point now. Hit the first focal point, and then it's going to come out parallel. All right, so let's see how well we did with this here. All right, here we go. Down to the focal point, hitting there. All the refraction right in the middle. Ooh, this is pretty good. Ooh, it's pretty good. Right through the middle. There's ray 3 happening right there. Wow, that's pretty good. I dig that. There's ray 3 happening right there. Yeah, those 3. I got that pretty good. You're not going to see that very often from me, maybe from a professional. These three all intersected right at the same image point, so yes, definitely our image is right there, and we can answer the 4 image questions that we are so familiar with by now, which is, number 1, is this a real image or is this a virtual image? Think carefully, is this real or virtual? Remember, our criterion was, do light rays actually form the image at the point where the image is? Another way to think about that would be if I took a screen, like I took a piece of paper here. I took a piece of paper. Could I catch the screen? Could I catch the image on the screen? Right? And in the case of a real image, the answer would be yes, because light's actually there. Light's actually making the image there. Okay? So this is a real image. This is a real image. Let's see, what other things do we want to talk about? It does seem to be inverted compared to the object, right? The object is, as I usually draw, is pointed upwards, and that is not, so this is inverted. It apparently looks minified. It's not the same size. This looks smaller, so I'm just going to go with that because I'm true to my diagrams, and that seemed to be an okay diagram. Last question, where is it? What's the image distance? Is it positive? Is it negative? Which side of the lens is it on? It turns out it's on the opposite side of the lens. Now remember, we are, as observers, we are now not on this side of the lens like we were with a mirror. Why? Because the mirror would have been bouncing the light back to us in the eye. This is a lens now, so we are looking this direction. Our eye would be here. Okay, our eye is there, and we're catching the rays in our eye here. Okay, so this is, if you like to think of it, it's on the opposite side of the lens than the object is, or if you want to think of it as behind the lens compared to the object, something like that. Okay, I'm going to put opposite side. It looks like it's a little closer to the lens than the object is. All right, so the object is far enough away such that the image distance is closer to the lens than the object is. Okay. Now, lo and behold, think back to the converging mirror. Did we or did we not have the converging mirror produce an image with the exact same answers to the 4 image questions? We did, didn't we? Right? If we did, then we should call this the same type of lens as the mirror. Okay? So if I had changed this into a mirror and I had the object this far away and I would have drawn my diagram, right? And then the image would have been here. Did I say that wrong? The object's far away. The image would be right in here, okay? And I would have answered the 4 image questions and come up with this. So this is an image with the same properties, being formed by a different physical process. That's why I call this a converging mirror, and I call it a converging, this is a lens, and I call the converging. If you call it by shape, then technically that would be the concave side, this would be the convex side, so really this is a double convex lens. Because it's shaped this way on both sides. So you wouldn't want to say that's a convex lens and a concave mirror, and then you'd think maybe they do different things. So, I don't know. It's just my peculiarity of naming things. I take a lot of, I put a lot of meaning into the naming of things, and it's just the way it goes. Now, think about what's going to happen to the image if I scoot the object further towards the focal point, but not past it. Okay? If I scoot the object closer here, where does the image go? Well, think about it. Ray 1 doesn't change, we know that. I'm gonna default to ray 3 in this case, because if I take the object and I scoot it here, the angle at which the ray has to go down through the focal point and then eventually contact the lens is gonna make it a much steeper dive, which means by the time it gets out of the lens, it's way down here, and that's gonna take a while for it to converge with ray 1. So if I scoot the object closer, rays 1 and 3 take longer to converge. So the image is moving away. And that's the exact same thing that happened in the converging mirror situation. All right? Now, if I scoot the image, if I scoot the object in past the focal point, remember we did this with the converging mirror. If I scoot the object inside the focal point, what happened with the mirror? Well, things changed, right? Things changed. We no longer had the ability to find a real image, okay? We had in fact, upright, magnified virtual image when we scooted the object inside the focal point. And if you don't remember that, go back and check. If we do that here, will we find the same thing? Well, that's the question, okay? So let's go here and here, and I'm going to put the focal points way over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm going to put the focal points like so, and we're going to start with an object within the focal point here, like that. Okay. Sorry about the glare, but that shouldn't affect us. All right. That hopefully won't affect us. Okay. I'm going to now try and draw the rays so that we locate the image. Okay, so let's do ray 1 here. Ray 1 comes in to the center of the lens, goes out through the focal point, which means it goes this way here. Like so, that's ray 1. Okay, ray 2 is going to, it can't come from the object and go through the focal point, so we have to pick the ray, if you remember this, we have to pick the ray that seems as though it came from the focal point. So we're picking the ray here, which is on this line right here, from the focal point to the top of the object. And it goes up. And at this point, you will notice that I have not drawn a big enough lens. That's okay, just assume that it's big enough, okay? And like I said, I have the benefit of grid lines here, so I know that I put the middle of my lens on this grid line right here, so I'm just gonna use all the refraction happening. At that point, this ray comes out parallel, which means it goes like this. And you can see that these are not going to converge on the viewer's side, but they will be diverging, just like these rays were effectively diverging by the time they hit the eye. My eye is out here, right? My eye's out there, and these rays are diverging by the time they hit my eye, so I'm tracing them back. That's what we'll do. We'll trace them back. And lo and behold, you already know that if I have to trace rays back, that must mean what type of image? I want that further. Whoops. Kind of that last one's up there, right there. Okay, there we go. Image is right there. I didn't hear anybody answer, so I'm going to go ahead and assume that in your mind you said virtual. This is a virtual image. If it's traced back, it's virtual. No light rays are here making this image. Note the difference. Light rays are actually converging here. No light is coming from this point or reaching this point. It's all smoke and mirrors. If we answer the 4 image questions about this one, yes, virtual, because we know we traced them back. Magnified is one of the main things that I notice about this. Upright is another thing I notice. And this one is not on the opposite side of the lens as the object. It's on the same side of the lens as the object is. So this is a magnifying glass. If you've ever used one of these, what you'll notice is if I have an object that's very far away, or like very far away, and I look through the magnifying glass, it could be fuzzy, blurry, weird looking, it could be upside down, okay? I bring it closer, 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 very fuzzy, all of a sudden, big, magnified, upright image, right? So if you look at something that's really tiny through a magnifying glass, that's the thing you're seeing right there, is that image of this object. So this is just your basic magnifying glass. Okay, let's do this. I'm gonna introduce the examples here at this point for these two situations because it seems like a good time to do that. If you go back and look at the video on deriving the mirror equation, right? We looked at angles, we looked at similar triangles, we looked at tangents and then opposites and adjacent sides. But if I unpack all of that, I'm going to get the exact same thing here. Now, I did this situation where we had a converging mirror and we had the height of this thing and the distance of that thing and the height of this thing, the distance of that thing. Well, it's exactly the same thing. It's just as if you took the image and just rolled it this way. Well, not rolled it, but like as if it was a page in a book. And it's over here now, right? There it is. All I did was just fold it across here. So by symmetry, these are going to be the exact same geometrical descriptions. Because you can see, if I pick ray number 2 here, it comes in at this angle, it goes out at that angle. I've got similar triangles, right? And then I've got the height of the image. Same thing here, when I look at this ray right here, it's going to have parallel angles across the symmetry axis, okay? Same geometry, same math. Same math leads to same relationships between the distances. Okay? So, if I do this, our object distance is DO, and that's here, and our image distance is DI, and that's to here. Like so. And that means that we're going to get the exact same relationship as we did before. So the thin lens equation equals the mirror equation. This is the wrong word. Thin. Thin lens. All right. All right. The thin lens equation is the mirror equation, and therefore I can write it in the exact same way because it has the exact same meaning. That relates to distances. We also had the magnification. That's also the same. The magnification is negative the image distance over the object distance, because ultimately we're interested in how much higher is the image than the object, or lower if you like, right? So really this also is the same as the image height or the object height. All right. Now, before we use these and do an example on this, I want to remind you of the sign convention. When we did mirrors, we had a sign convention. The sign convention, I don't know how you felt about the sign convention, because ultimately we don't really talk that much. So I figure that everything's great. But I do know that the sign convention sometimes causes problems. So let's just go over it here. If you recall with the mirrors, we said that any image which was created on the same side of the mirror as the object was is positive, right? Remember how we defined these like spaces? And let's see, maybe I have a little bit of room. Can I just kind of go up here and get rid of this for a sec? Okay, so quick recap here. If I think about the mirror as being here, this was the positive side. This is the real side. Real, and we said real was positive, and this was virtual. And we said that was the negative side. Let's see. Oh, well, that has basically no chance of you possibly seeing that. Let's try a different one. All right, we'll go again. Okay. Rewind. Here we go. If I had a mirror that looked like this, oh, much better. We defined this to be the real side, which we called positive, and we said this was the virtual side, which we said was negative. Oh, that's a little better. Now, it was the same no matter what the curvature of the mirror was, whether it was curved that way, this way, whatever, plane, doesn't matter. Okay. So, we have to flip those. Because by definition, the real image here in the lens is made on the other side of the lens than the object is, because that's where the light's going. So I introduced to you the mentality that I use for this. And by the way, if you like it, great, use it. If you don't like it, throw it away and find your own way of doing things. That's great. This is how learning and pushing forwards of a subject happens. And one of the most important things that you can ever feel like you can do is tell an expert that he's full of garbage, right? Yeah, you should do that. It does happen every now and again. Nonetheless, we have to change our orientation of the sign convention. We're not changing the sign convention. We're sticking with real being positive, virtual being negative. But now we have to flip them around. Now with the lens, okay, this was the mirror situation, so I'm going to put that up here. This is the mirror situation. The lens situation is that the real side is over here, and the virtual side is now over here. Now back to the mentality that I was going to tell you. The mentality I have for this, how do you know? Okay, well, do you want to think about this being this way and that being that way? And I remember that they're flipped back and forth from one another, but I can't remember what's what. Okay. Here's how I think about it. What is the light supposed to be doing? If it's a mirror, the light is supposed to be bouncing off the mirror. So, if I have light bouncing off a mirror, all the light's over here. Light's over there. If light's doing that and the image is over there, that's the positive side. That's light doing what light is supposed to be doing, right? According to us. There's no light on this side. If there's an image over here, it's not because light is making it here. Okay? It's because we're perceiving it because of diverging rays this way. So if the image is here, it's because light made it, and that's what we want light to do. Think about that with the lens situation. What is light supposed to do? Light is supposed to go through a lens. It's supposed to come through a lens. It's not supposed to make images on this side. That's the virtual side then. It's supposed to come over here and make a real image over here, and it did right here, so this is a real image. It's on the positive side. Okay, so I think about the mentality of where is the light supposed to be? If it makes an image on the light on the side that it's supposed to be, we call that a positive image. Okay, that's the real side. If it does the opposite, like this up here, this is a virtual image. It's on the wrong side, quote unquote, wrong side. There's no right or wrong side, but it's on the one that we kind of go, huh? Why is there an image there? The light's all over here now, right? Making it like going over there. Well, I mean, light's coming this way, but the light's supposed to be making an image over here. Okay, so that's the negative side if it makes an image on this side of the lens. All right. So if we take that as our sign convention mentality, then we can go ahead and do the same type of thing. Suppose that we have a lens here and it's got a 10 centimeter focal length, and we have an object that is 30 centimeters away. Okay. Now with focal lengths, okay, we're gonna have this from 10 centimeter focal length. Focal length lens. Now, right here, we don't know what kind of lens it is. If I just tell you the lens got a focal length at 10 centimeters, well, could it be a converging lens? Could it be a diverging lens? Okay, we don't know. But because of the naming scheme, converging mirrors do the same thing as converging lenses, right? There's a overlap here. Remember, we called the converging mirror having a positive focal length. And we did that because the focal length was on the real side of things. Well, here, a little bit murky. I got a focal length on both sides. Well, this is the real side, that's the virtual side. So what's the focal length? Okay, is it positive or negative? Because it's a converging lens, it does the same thing as a converging mirror. A converging mirror has a positive focal length, therefore this has a positive focal length. So if I tell you plus, then you know that one. Focal length is greater than 0 if it's a converging lens, just like when it was a converging mirror. Now, you have a couple of mentalities available if you would like. How do you remember that? Well, I remember it because I named them the same thing. So that's how I remember it. Now, if you don't call them the same thing, you may need to either remember, oh yeah, if it's a one of those, then it does a one of these. One of the other things to do is think about, okay, well, if the, let's see, if the focal point that light, no, wait a second, if I'm getting this right or wrong. Yes. Now, if the focal point that light, no, go backwards. If the side of the lens that the light hits first has a focal point on the same side of it, then that's like a diverging sense. If the side of the lens that the light hits first has a focal length that's on the opposite side of it, then that's got a positive focal length, right? So can you, how convoluted do you want to be? That's like, I personally don't like that as a rule. But if light hits the side of the lens here first, and the focal length's on the other side of the lens, then this is the convention. Okay, or just call it converging and make it positive. Let's find the image here. Let's find the image, where is it, and let's find its magnification. The same thing. This is not going to be like, oh my gosh, this is all brand new. You do the same exact thing with the mirror equation. Algebra is all the same, right? I would have said, all right, I want to find the image distance. I know the focal length. I know the object distance. Therefore, I'm going to go 1 over 10 minus 1 over 30, which is going to give me 2 over 30, and my image distance is going to be 15 centimeters. It's going to be plus 15 centimeters. Did I do that right? That's going to be 3 over 30, 3 minus 1, 2, 30, yeah, okay. So 15 centimeters. Is that copacetic with what we're seeing? Well, this is kind of backwards. I said 10 centimeters and... No, that's the focal length. This is 30 centimeters. Oh, this is great, because look how big focal length, look how big the object distance is here, and look how small the image distance is. Yeah, that works. My diagram's actually kind of good. It's not exactly scaled, but it gives you the right flavor. Let's see. If the object is 30 centimeters away and the image is 15, what kind of magnification are we going to be getting here? We are going to be getting magnification equal to negative di over do, and that means negative 15 over 30, so that's minus 1/2. Yeah, that's a minified image. Okay, good. I feel good about that. This is definitely a smaller image than the object. The height is less. Remember, it comes with two pieces of information in the magnification. The 1/2 tells us the relative scaling of the height of the image compared to the object. And of course, the negative sign tells us it's inverted. Positive would be upright. I do this, but it's because I always draw the object as upright. It's got the same orientation as the object, if it's positive. Negative, opposite orientation of the object. Yeah? Okay, so, happy days. If I did the opposite and I said, look, I've got a plus 10 centimeter lens, but the object is 8 centimeters away, then I'd have this situation here. I'd have the object scooted inside the focal point. So 10 and 8, what you can do, I mean, I can make up a calculation here for you, but ultimately, right, it's exactly the same thing as we did with the mirrors. I would put in 10, I would put in 8, I'd find I'm going to get a negative image distance. That's ding, check, because when I drew this, negative side is over here, real side, positive, is over here. So negative image distance checks. I'm going to get a magnification that would be positive now because my image distance is negative. Positive, upright. Image, object, same orientation. That checks. I can't quite argue the size of it, but you'll find a positive magnification that is greater than 1, and that was going to tell you that you have a magnified image here. So just look back at the example we did with the mirrors. It's the same exact example. Nothing different. Okay, so what I want to do now is get onto the diverging lens. Yeah, I think that's what we're going to do. We're going to get onto the diverging lens. Yep, let's do this. Now, what's fun about a diverging lens and a converging lens, oh, I didn't bring in the, oh well, is because if you took a block like this and I wanted to cut a shape like this, right? I'd cut a shape, I could cut that shape out of here, right? I could cut that shape. It would look like this if I just cut it right in the middle. But what would that leave on the other side? Let's see if I can sketch that for you. If I tried to draw, oh, actually, I'm just going to draw a block around this thing. Look, imagine if my block was this, right? If my block was that, and I cut the converging mirror out of it, what does that leave me with? Well, it leaves me with this piece here and this piece here. Kind of fun. If I take those two pieces and I flip them around and glue them together this way, I get a diverging lens. The diverging lens, notice that the converging lens is thicker in the middle, thinner at the ends, at the top and bottom, opposite for the diverging lens. Okay, the diverging lens is thin in the middle and thicker at the top and bottom. It's got that hourglass shape to it, right? If I take these two pieces, right, they're thicker on the top and they're thinner in the middle, right here. And I'm just going to take them and put them together. So that's what my diverging lens looks like. We'll do the same thing as we did before by trying to go through and use our mentality of what do the three rays tell us. How to draw the three rays, we have to just be flexible with But what are the rays ultimately telling us? Here is our axis. Like so. Again, I have two curved surfaces, and both of them have a radius. Therefore, both of them have a focal point. Let's put the focal points here and here. Let's go here. Focal point there. 1, 2, 3. 1, 2, 3, 4 here. Focal point there, focal point there. Does that look about right? Sure. Okay, let's do object over here on the left. There's our object. 3 light rays. Okay, 3 light rays. So let's take a look at ray number 1. Now, what do I want to say about this? We're doing basically the same thing as we did in the diverging mirror case. Oh, before I do this, I will note diverging lens has a focal length that is less than 0 by convention, because it has the same focal length convention as the diverging mirror. Nonetheless, let's take a look at what the rays are telling us here. Okay, I'm going to go in straight with the axis, or I should say parallel with the axis here, all the way to the center of the lens. And you're going to say, well, wait a minute. I have a focal point right here on this side. It's right there. How is the light just, why isn't it just going to do the exact same thing as it did with the converging mirror, converging lens? There's a focal point. Why, right? What happens? Light comes in parallel and it goes through the focal point. Okay, but if it did that, then this wouldn't really be a diverging lens, would it now? It wouldn't be. Let's take another look at a close-up of the top of that one, just like we looked at a close-up of the converging lens. Right? Closer view. Let's move closer. Here's the top of the diverging lens, like this. All right, there's the top of it. A ray of light's coming in. It's coming in at some angle from over here. Here it goes. It's going like this. I'm going to drop a normal onto this surface. I don't really like that too much, but okay, I'm going to drop a normal onto the surface. Where's my, here's, do this one. I'm going to drop a normal onto this, so it's going to go right about here. Right about there. There's the normal to that surface. It's about that. Now, remember, when light goes from air into glass, it bends towards the normal. So it's already pretty close to the normal here by the time it gets there. So it's going to go even closer, which means that it's kind of going, it's not going straight, it's going this way, like that. Oh, you can't hardly see the difference in this. Let me take some of this normal away here. Okay, let me do, you know what? Let me do this again. Okay, let's try this again. All right, just got a little too busy right there. All right, so here, let's suppose we got a light ray coming in. Let's actually pick a direction here. Let's go here. I got a normal right here. Okay, so there's a normal. All right, I'm gonna have light hit that normal from, say, this side here, like that. Light's hitting the normal light's hitting that point, not hitting the normal. Like that. Here comes my incoming light beam. It hits that point. It refracts closer to the normal. Okay? It refracts closer to the normal. So that means it's coming in here and it's going to go, instead of going straight along this right here, it's kind of going closer to the normal, so it's going a little bit more like that. Like this. right? It's bending towards the normal. Now, when it gets to this side, remember it's going glass to air. Here's the normal like so. It's going glass to air, which means it's going away from the normal. So it was traveling along a path like this. Now it's going away even further. It's going this way. Right? In other words, look at what's happening. The light was coming along this direction, and now it's going along that direction. It's diverging. Right? It's getting more divergent. That would mean that if we picked this as the focal point to use with the incoming ray, we would be not doing what a diverging lens is supposed to be doing. The diverging lens is supposed to be diverging the light. So we have to use the first focal point, this one over here. Just like we did with the diverging mirror, we were going to take a look at the ray leaving the lens as if it came from the focal point on this side. So the ray goes like this. It goes as if it came from this focal point. Why? Because it's diverging them. So be aware. This is a common pitfall, okay? That you see the focal point over here and you go, oh, I'm just going to... not with the diverging lens. Okay. Now I've used that focal point. Now I got to go through, do the other ones. Check this out. This is ray 1 here, by the way. Ray 1 is right there. Ray 2 comes straight through the middle of the lens, just like the last one did. Nothing different there. Just like that. There's ray 2. Ray 3 can't use this focal point because we already used it. So I gotta remember to go to the other focal point and aim at it. If I aim at this focal point with ray 3, I'm never gonna reach it, but I'm gonna come out parallel. Like so. There's ray 3. Okay, so you should see that all three of these rays kind of trace this one back here, intersects right about there. There's the image. Right there. If I got it darkened in enough for you. Right there. Can you see that? Just barely. Yeah, it's small. But, you know, that's what you expect. It's a diverging lens. That means it has all the properties of the diverging mirror. The diverging mirror. What did we have with the diverging mirror? Going back in time. Beep, 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 beep. Oh, we had virtual images. Ding, virtual image. It's on the same side as the object, right? On the behind the lens, if you like. Ding, ding, ding. Minified. Upright. Small focal distance. Or, small image distance. Yeah, we check all those boxes right here, right? Virtual image. Minified. Upright. Same side. That's the different part, but that's okay. Same side as the object, right? Same side. Oh, I erased the one up here, but same side as the other virtual image that we had. See, I have it written here. Same side. We checked all those same exact boxes with the diverging mirror, all right? Suppose if I did the same exact thing as I did before, I have a 30 centimeter object distance and now I have a minus 10 centimeter lens. Let's see what happens in that case. All right, so object at 30 centimeters from a diverging lens of focal length 10 centimeters. All right, so here's one of those wordings that I'm putting a little bit of the responsibility on you. Object at 30 centimeters from a diverging lens whose focal length is 10 centimeters. Bum, bum, bum. You gotta compute this right here. See that right there? It's nice. It's a two-dimensional screen. I keep forgetting because this is 3 space. So I could put my finger right over here, or I could put it way back over here. I gotta try and remember I can do that. You have to put the minus in on the focal length in these cases if I say something like this. Okay, if we do the same thing, find the image distance, find the magnification. In this case, it's going to be equal to 1 over, you must keep the minus in with the calculation, minus 10 minus 1 over 30. You can see without a doubt this is going to come out to be a negative number, right? I got a minus, minus positive. So we're going to do the same thing. We're going to go 3/30ths, and we're going to go minus 3 minus 1, which is minus 4, so minus 4/30ths, and that means 7.5. So that means negative 7.5 centimeters. 30/4, that's the same as 15 halves. If I look at the magnification, minus di over do is going to turn into negative 7.5 centimeters over 30 centimeters. This is going to be a quite nicely minified object. It is going to be upright because those two minuses are canceling each other, right? Positive, positive, right there. Okay, 7.5 over 30 is the same thing as 30 divided by 4 divided by 30, so the magnification is plus 1/4. Okay, and that checks with what we see here. I don't know if it's 1/4, but it shouldn't be because the image distance is not what, or the object distance is not what it should be. But the point is, when you keep that minus sign, everything works out just fine in here. But you got to remember, if you get a situation where you're told something like this, you put the minus sign into the focal length, you got to keep it, right? You got to keep the focal length with the negative right here. Otherwise, you're going to end up with the exact same calculation of it as if it was a converging lens. All right. Okay. So that's the situation with lenses. That's all I'm going to really spend time on with this because I'm telling you, it's exactly the same as mirrors. So as long as, actually what you can do is use this as kind of a review for some of the mirror stuff. And the ray is a curved mirror stuff. It's very much similar. Okay. I really encourage that mentality of think about the sign convention as being the thing where the light's doing what it's supposed to do on the side of the thing that it's supposed to be doing it on. Okay. A lens passes light through it. It's transparent, whereas a mirror is silvered and reflective, so light bounces, right? The light's always over on this side. If it's a lens, the light's always coming from here and going that way. Okay, so you expect that side to be the side where the image is formed. So keep with where is light supposed to be going? What's it supposed to be doing? That's the positive side. The other side, negative. Okay, so we've got that. Let's see here. What I want to do, so this is all kind of leading up to partially, well, let's see, I'll give you a little bit of a preview here. The class tomorrow is going to talk about a higher plane of thinking. We're going to transcend these laws, and we're going to be exposed to a way of thinking such that the laws that we're dealing with are evident. And this is just beautiful. Okay, so we'll talk about that. We'll talk also about how to construct lenses. Were you to want to say, look, I've got this piece of glass, I want to grind a radius onto one side of it, and I want to grind this radius onto the other side of it and make myself a lens. How would you do that? What would you have to not literally how do I make my machine work, but how do I choose a radius on this side and this side such that I get a focal length that I wanted to achieve, okay? So we'll talk about that also tomorrow. Now, beginning next week, yes, next week is the 9th, the week of the 9th. So next week, Tuesday, it wouldn't matter on Monday. So Tuesday, starting next week, we'll talk about now taking mirrors and lenses and putting them together to make instruments. Okay, so I'm not spending a lot of time doing lens diagrams and lens equations here because ultimately, like I said, they're all the same as they were for mirrors, and we're also going to get the added benefit of going back to the mirrors and then going back to the lenses and putting them, what happens if I have an optical system? What if I make a camera? What if I look at a telescope? How do I make a microscope? Putting lenses and mirrors in combination with one another. So we're going to be using these things again starting next week when we start looking at optical instruments. So that's a little bit of a preview of what's going on. As far as today, this is Wednesday. The quiz is due today, so you please do that and be aware of that today. Hopefully you managed to get your lab turned in by yesterday. Forgot to mention that yesterday, but hopefully that happened. We will have lab again this coming Friday in a couple days, and by then hopefully get a lab kit. We will be using lab equipment from the lab kits, and PLC is also due on Friday of this week. So with that being said, keep working on the homework. That's going to be due Tuesday of next week, and things are kind of starting to get rolling here, okay? So keep on top of the assignments. That's the best way for you not to fall behind in a class like this, and all of a sudden, in a couple of weeks, it's going to be too late. So stay on top of the assignments, keep working. If you have any questions, please let me know. And in the meantime, I will catch you next time for stay tuned for our next video on the principle by which reflection and refraction become evident. All righty? So we'll talk to you then. Have a great rest of your day.